Okay. I think now we can get started. And looks like there's a bug here. Fixing it takes time. Okay. So we'll talk about interconnection networks today. I wish I had a lab for you to do on interconnection networks, but maybe when you take 742, you'll do it. A reminder, you have one more lab, hopefully the most exciting lab. It's on cache coherence in multi-core systems. You'll be implementing the Mezi cache coherence protocol, and hopefully some of you have started. Who has started? Good there. Health started. Health started also. Please get started. It's due on May 9th, and that's the latest time after latest time we will accept submissions. There is no extra credit for this lab. You could do it if you want. You could optimize the protocol. For example, you could do cache-to-cache transfers, but I wouldn't recommend starting that way. Just implement what is given, because even that will take some time. Cache coherence is one of the most complicated parts of a multi-core processor, because there are a lot of race conditions that you will see that you will need to handle also when you do this lab. You don't want two cache blocks to be in different states in different caches, so you'll need to ensure that that doesn't happen. So try not to jump into the extra credit. There's no extra credit, but if you do something, let me know. Okay? Well, this is old information. Well, okay. I guess I forgot to remove that. Well, this is 7 days. That's right, actually. This is not old. Because originally we said May 2nd. Right. We're basically what we're doing is we're granting an automatic 7-day extension to everyone, right? Instead of asking for you to submit everything on May 2nd. But there are no other late days accepted. And this is what you're going to implement, as you've seen before. Have you seen this before? Not yet, right? This is a great distribution for midterm too. I thought it would be better, but at least we're moving towards the right-hand side of this. I hope the final will be better. I thought this was shorter than the first midterm. Was it? Yes? Okay, I see nods, so that's good. Well, you will get your exams later today. Okay. Okay. Okay, that sounds good. So you will get the exams later today, hopefully. But the solutions should be up on the website.
Yeah, everything is up.
Okay, you can take a look at the solutions. Know the solutions for the final exam. I think some of the problems were pretty challenging in my opinion, but they're good problems. They test your understanding. So know the solution to all of the problems. And if you're worried about your grade, just talk with me. Wednesday during my office hours is the best time. And you can go to TA's office hours to go over the solutions to the exam. Actually, there was a review session with the solutions, right? Okay. And these are the statistics. There's a big spread. I would like the minimum to go up a little bit, yes.
Can you post the solutions to the website?
Oh, it is posted right now. Yes. Yeah. It should be, I think. I haven't checked, but Rachada tells me that it's posted. Okay. Okay, that's good. Okay. Well, if you haven't done well, this doesn't mean that's the end of the world. There's a final exam, and there's one more lab. So definitely focus on the final exam. Well, speaking of which, we'll have it on May 6th. And this is not the time I scheduled, but that's the time we were assigned. I don't particularly like that early in the morning. I'm not sure if you guys like it, but that's what we were given. It's going to be 8:30 to 11:30 a.m. And we're going to move to a different place. So hopefully that change will help you. We're going to move to Hammerschlag Hall B103, which is the big auditorium on floor B, instead of being squished here for three hours. It's going to be comprehensive. All topics in the course will be there. You already know that. We're going to allow 3 cheat sheets, and we might have a review session. Do you guys want a review session? How many of you do? Say it again?
Lecture or outside of lecture?
Outside of lecture, probably. Because we still need to do 2 more lectures. Yes? So who says yes given this new piece of information? Who says no review session, I don't want any of it? I'm sick of this. I know. I know you're not saying you're sick of this here. But you don't necessarily want it. Okay. So remember, this is 25% of your grade. It's 1/4, so it's important to do well. I will definitely take into account your improvement over the course. Everything is curved, and some of you have asked questions like, what if people drop? I do include them in the curve. There have been people who have dropped the course, but they're not necessarily in this distribution over here. Otherwise, you would have some zeros over here. But I do include them in the curve. So it's everyone who started the course. So you guys are the ones that are sticking with it. So that shows something also. I will definitely take into account your improvement over the course too. If you've gotten zeros on the first 2 exams, and if you aced the final exam, that's a big improvement, I think. And we will definitely take that into account. And I mean, I don't need to tell you that because we've talked about the exam. Same advice. I'll give you the same advice I've given you for midterms 1 and 2. I'll talk about this later also. But I'm teaching parallel computer architecture next semester. Several of you asked me whether you can take it. What will it be? Basically, it will be computer architecture, and it's the next step after this. It's a deep dive into many topics we covered. It's going to be a more research-oriented course. And many topics we did not cover will be covered over there, like multi-threading will be covered in a lot more depth. Interconnects will be covered in a lot more depth. We'll start that today. But it'll be a lot of paper reading and paper analysis. So you'll need to be very critical about what's written in the papers, and you'll need to criticize them. You'll need to do reviews. It's going to be research-oriented in the sense that there will be an open-ended research project also. So everything you've seen and some other things maybe you have not seen, we'll give you some topics such that you can propose some research that you're going to do over the course of a semester. And many people have done research in these courses, in these graduate courses, and have published papers at top venues. So if you're interested in something like that, this is one of the courses that you might want to take. And it'll be on cutting-edge research and topics in the hardware-software interface. Similarly to this course. We won't cover pipelining, for example. Pipelining we will assume. Caches we will assume. We will cover advanced caching mechanisms. DRAM background we'll assume. So if you're enjoying 447 and are doing well, you can take it. You don't need to have taken 640 and 740, even though that's probably listed as a prerequisite. We need to change that prerequisite. If you've taken 447, you'll be well prepared for 742. But talk with me if you want to take it, if you want advice. And also, if you're excited about computer architecture research or design, or looking for a job or internship in this area, you can definitely talk with me. Several of you have talked with me already. And I think some of you have found internships too, which is good. But I'm happy to talk with you about this. Okay. So let's jump into the lecture. If you have any questions on 742, you can ask me later. Hopefully we'll dedicate some time on Friday so that you can ask me some more questions, but we'll see. So last 2 lectures, we've started multiprocessors. We talked about bottlenecks in parallel processing. We had a bonus question on that in the exam, on Amdahl's law mainly. We talked about multiprocessor correctness, sequential consistency, and weaker consistency models, and we talked about cache coherence, and you'll be implementing this. We talked about a lot of trade-offs in cache coherence, which was interesting. Today we're going to wrap up cache coherence. We're going to go through that really quickly, hopefully. And we're going to start and finish interconnection networks. I don't intend to spend more than 1 lecture on this, even though it's a huge topic. I mean, you could have a class on interconnection networks. Because it's important. Communication is important. Remember when we started computer architecture, we talked about 3 components of a computing system. Computation, which is the processing element, which we've covered early on. Communication, which is this. And then storage or memory. We've covered storage or memory in a lot of depth. You've covered computation in a lot of depth, a lot of ILP extraction mechanisms, SIMD execution models, out-of-order execution, pipelining, all of that is part of computation unit design. We've covered memory in a lot of depth, but we haven't covered communication in a lot of depth. We just don't have enough lectures to cover everything in a lot of depth. So this will be our in-depth coverage today. These are some of the readings. I'll just remind you. These, you can take a look at them later. So let's continue on cache coherence. This is what you'll be doing. And what you'll be doing is actually not isolated from reality. actually nothing you did in this course is isolated from reality. This is the cache coherence protocol that's very similar to what was implemented in Pentium Pro, Intel Pentium Pro. And in many processors today, you see a very similar protocol, except it's more complicated. You may have an O state over here. This was, I think, one of the last slides I left you with. Basically, the trade-offs between Snoopy cache, Snoopy bus-based protocols versus directory-based coherence protocols. So know this well. Basically, if you have a Snoopy cache protocol, missed latency is short. Basically, when you get a request, that goes as a bus transaction to memory, and everybody sees it. And that's how you maintain coherence. Whereas the downside of directory is it adds this indirection to this missed latency. You have to go to this directory first to figure out who else has it and ensure coherence. Only after that you can get the data. So there's this extra step. And we talked about other upsides and downsides. The big downside of the Snoopy cache-based protocol is it relies on broadcast messages seen by all caches, which means that it relies on a single point of serialization for everything, basically a bus. So it's not very scalable. Whereas directory is much more scalable because you can actually distribute the single point of serialization across different nodes, and everybody knows which node to send the request to, such that it gets permissions from the directory. So it's much more scalable. It doesn't require broadcast to all caches. And it's exactly as scalable as the interconnect and directory storage. And we'll talk about the interconnect, how scalable we can make it later. So let's revisit this directory-based cache coherence, because this will kind of motivate some of the interconnects that we will talk about. Although cache coherence is the only one type of traffic that's carried on an interconnect in a multiprocessor system. We talk about directory, so you know all of this, right? You have a logically central directory that keeps track of where the copies of each block actually reside. And when a cache requires that block, it consults this directory to ensure coherence. And directory ensures coherence. I'm not going to go over this. You had a question on the potpourri related to the calculating the number of processors in the directory. But basically, these protocols are usually required when scaling past the capacity of a single bus. Single bus is not scalable, as we will again see later, because as you put more processors or more caches hanging off the bus, you increase contention, because you can transmit only one thing on the bus. When one processor is transmitting, the other processor needs to wait. Right? So it's not scalable in terms of a bandwidth perspective. You can pipeline the bus and increase that, but still it's limited. And the second is it's not scalable from an electrical perspective as well, because as you add more things hanging off this bus, you increase the electrical loading. As a result, you get lower frequency and reliability issues if you want to run it at high frequency. So directory-based protocols can be distributed, as we've discussed. But coherence still requires a single point of serialization to ensure write serialization for a particular cache block. But that single point of serialization can be different for every cache block. Right? Well, this is the second one. You can actually stripe things across nodes, right? And as we've discussed earlier, if you have, let's say, 1,000 processors, you can have directory divided into 1,000 across all of those nodes. Right? You can have 1/1000th of the directory over here, the other 1/1000th of the directory here, ... And whenever a processor requests an address A, basically it knows which directory node it needs to send the coherence request to, like read, exclusive, or write, and then that gets routed over the interconnect. Well, to motivate this, basically, you need some kind of interconnect to connect these processors, and that's what we will talk about next. But let's take a look at what we can do with this directory. We can actually reason about the protocol for a single block when you have a directory. Basically, you can think of the directory node as a server, and you can think of the private cache as the clients. Basically, this is the directory node for address A, and many clients can be requesting this address A, the block A. Right? And directory receives read and reads exclusive requests for that address and sends invalidation requests, or maybe other requests, as we will see later. Basically, invalidation is explicit in this case, as opposed to Snoopy bus mechanism. Invalidation in Snoopy bus is implicit. When a cache actually snoops a read exclusive request, it invalidates its copy, right? So there are a bunch of basic operations. I'm going to go through this relatively quickly because it's very simple, I think. The basic operations follow the semantics of the Snoop-based system, but everything is explicit in this case with the request-reply messages. In Snoopy caches, everything is implicit, right? You just compare the address and look at what the request is on the bus. The directory receives read exclusive and upgrade requests from nodes and sends invalidation and downgrade messages to sharers if needed. And it can forward the request to memory if needed, right? Because if no one has the data and data is in memory, it needs to fetch the data from memory and send it back to the requester. And it replies to the requester and updates the sharing state. This makes protocol design very flexible because everything is based on these messages, right? Everything is based on these explicit request and reply messages or some other control messages like invalidation. Why is the protocol design flexible? Because depending on your implementation, you can change the forwarding paths. The directory can say, and you can, as long as you add the appropriate control messages, the directory can know exactly where a cache block resides. For example, let's take a look at this. Let's say we have this kind of system. And these two blocks, you have this processor 0, processor 1, and they're connected with some kind of a mesh network, let's say. Basically, you have 16 processors in this case. Well, I guess I'll draw all of them. You could scale it also. And they're connected through this mesh network, which I'm not drawing over here. But directory is distributed across these nodes. So I mark these as the directory. Let's say processor 0 wants to access address A, and processor 1 has the address A modified in its cache. The processor 0 doesn't have the address because this is modified in processor 1's cache. Processor 0 sends a request to the directory node that actually has the directory state information for address A. Let's assume that it's here. This is the directory node that contains address A. Processor 0 sends a message. Directory node exactly knows which other processor actually has address A. So the directory node, what it can do is it can take a shortcut, right? It can say, oh, I know that processor 1 actually has this address A, so I'm going to instruct processor 1 to send its data to processor 0. Right? Why might you want to do this? Well, because these are very close to each other, right? In terms of proximity. Another potential, the simplest option would be for the directory to say, processor 1, give me the data, I'm going to send it back to processor 0. That'll take a long time, right? Because processor 1 sends the data. First of all, directory requests the data, processor 1 sends the data, and then directory sends the data back to processor 0. That's a lot. Instead, you can design a protocol where directory immediately recognizes that processor 1 and processor 0 are so close to each other, so it can say, processor 1, send address A to processor 0 and update your state accordingly because you will both be sharing the data. Or also send me a copy of the data at the same time such that everybody will be in shared state. So you can do these optimizations if you have explicit request and reply messages. So that's why this is much more flexible and scalable compared to a bus-based protocol. That's the cache-to-cache transfer that I mentioned over here. Okay, let's take a look at some transactions. This is a Mezi-based directory protocol. Mezi is a protocol that can be implemented with bus-based, Snoopy-based coherence or directory-based coherence. I think this is the example that I gave you, but let's see. Let's say processor 0 acquires an address for reading. It sends a read request, and the directory sends it as either exclusive or shared state to processor 0. What it can do is it can actually send it if no other cache has it, it can send the data this way. But if processor 1 has the data, just like over here, it can send a message to processor 1, and processor 1 can supply the data to processor 0. Let's take a look at another case. Processor 0 requests a data block in an exclusive fashion from the directory. Directory can send an invalidation to the owner of the block at that point in time. Owner invalidates it. It basically sends a revision, which is the data that it has in modified state to the directory. It can also, at the same time, supply the data to processor 0. So that's another way of doing this. This is more consistent with what I showed you over here. You can come up with all of these kinds of scenarios, right? And these nodes can be in different locations. This makes sense, especially if the owner is close to processor 0, right? It may not make sense if the owner is over here, closer to the directory. Then the owner may send the data to the home node, basically the the directory node that houses that address that's requested, and then the home node can send the data after that to processor 0 that requested it. So these optimizations all depend on where these nodes are distributed, right? You can think of a very large multiprocessor system where interconnect delays are very long, and then this starts mattering. You may want to do these optimizations. In fact, these things can be in different data centers also, right? So if you have coherence across the data centers. That may be a tough thing to do, but people have tried to build multiprocessors that are very, very large scale, like on the order of tens of thousands of processors with cache coherence. So one interesting thing, this is the last thing I'll cover, I think, in terms of these scenarios, is contention resolution. Let's say you have processor 0 and processor 1, they both want an address at the same time, and they want it in an exclusive state. Home node receives these requests, maybe at the same time. It basically can grant only one, right? You cannot give the data in an exclusive, an address in an exclusive state to both nodes. So let's assume that it selects processor 0, sends the data over there. What does it need to do to processor 1? Well, it can say, processor 1, too bad, I gave the block to someone else. This is one option, right? It can NAC. It's called a negative acknowledgement. Instead of acknowledging, it can send a negative acknowledgement. By the way, we discussed that you need to have acknowledgements actually for this to work, right? Whenever you send an invalidate, you need to wait for the acknowledgements. Otherwise, you can run into race conditions. And you can think about that on your own. So in this case, processor 1 needs to be NAC'd. There are other solutions for this too, which we will cover. Later, well, this processor is happy, this processor is unhappy. Later, processor 1 needs to request again, right? Because it's stalled, it's waiting. And then it requests again, and the home node sends the invalidation to processor 0. Processor 0 can send the data back to the home as well as to processor 1. Again, this depends on how close processor 0 and processor 1 are to each other in terms of latency. Now, you don't need to actually do a NAC. Now processor 1 becomes happy. But you could actually imagine that many processors can request the same node at the same time, right? If you're synchronizing on a lock, for example, everybody can be testing that lock and requesting that lock. So you could get a lot of contention in the home node. So this invalidation traffic can still be a lot if you have like thousands of processors and they're synchronizing at the same time. Think of barrier synchronization, for example. You have thousands of processors, they're all arriving at a barrier at the same time. They all need to check whether all processors have arrived at the barrier, right? Which means that and barrier is implemented as an address, right? It's basically a counter at an address. It basically counts how many processors have actually already arrived at that location. And all of the processors need to check that, because if that count is equal to the total number of processors that need to synchronize, then they can move on to the next task. That's a lot of synchronization that happens, especially when all of the processors get to the barrier at the same time. They all request that address where the barrier is housed them. So this is actually an interesting problem to how to optimize this, how to make this work. Actually, national labs are very interested in this kind of problem because they have these huge supercomputers that solve scientific problems or any kind of problems that are difficult. Weather prediction is one example, actually. I guess development of bombs is another example, or plane simulations. These are problems that require a lot of processing. And you parallelize your program, and you have this computer that needs to synchronize at an address. And you get all of this invalidation traffic that wastes energy as well as reduces your performance. So how to do this efficiently is an interesting problem. And it's going to be more interesting going forward as we have multi-cores that scale to higher and higher core counts. Okay, so I've given you one example over here, NACing processor 1, but that's not the only option, right? You could actually either NAC or in the case where you NAC or drop the request and tell the sender you should send again, the requester needs to retry. Or you can buffer the requests, right? The home node can actually receive all of the requests and have a buffer in which it serves the requests. This may be more scalable and more fair because now it knows in which order the requests have arrived, right? The requester doesn't need to retry. If the requester retries, then you have a lot of you might have a lot of new traffic that comes into the network. Whereas if you buffer the request, then the requester doesn't need to send another request, right? You can save some bandwidth. The downside with the second, or you can use the combination, right? If the buffer is full, then you can send a NAC. The downside of buffering is you may need to have a large buffer, right? If 10,000 processors are requesting a memory location, Well, you need a 10,000 entry buffer in the worst case for that particular memory address. And if you have lots of memory addresses, that's 10,000 times the number of blocks in your memory. That's just is not realistic, right? That's why many systems use a combination of these two things. Fairness is an issue. Like, who do you grant this? Which requester should be preferred in a conflict? So protocols need to take this into account. And in this case, both interconnect delivery order and the distance matter, and how you handle these also matter. If you keep knacking, for example, it may be that a requester that's farther away will get starved, because when you knack that requester will receive the knack late, and it also sends its next request late, and by the time it sends its request, someone else might have gotten the block, right? Too bad. So this is an interesting issue when you're designing a large-scale multiprocessor. Preventing ping-ponging is important. We've discussed ping-ponging, right? Ping-ponging is the problem where a cache block travels across different caches and ping-pongs between those different caches. This can be achieved with better synchronization mechanisms, such that you don't ping-pong a lot, or better prediction mechanisms. But you predict, basically. One solution could be, for example, you predict who will request this block next and supply this block to them. And if you have buffering over here, you could do that, right? Okay. We'll not talk about that in more detail. But hopefully this gives you an idea of the scale, of how a directory-based protocol should scale to if you have actually tens of thousands of processors. All of these issues become important and difficult to solve. So some questions, I don't think I'll give you the answers, but I'll let you think about them. How large is the directory? Well, you had a question on this. It could be very large, and our next slide will cover how can you reduce the size of this, right? If you have 64K processors, that's a lot of entries per block, right? And you've already calculated this in your exam. If you haven't, I would suggest you calculate it. How do you reduce the access latency to the directory? We have not talked about this actually as much. It's not only the size, but it's also the latency, right? Because let's assume that this is a 64K node processor, and the directory, this processor is requesting address A, and address A happens to be over here. The directory node for that address A, home node for this address A, happens to be over here. Well, you need to request it. It takes a long time to even request that, the coherence state of that node, right? Well, how do you reduce the access latency? Any ideas? How do you reduce memory latency in general? We've covered 4 techniques. Reduce/tolerate. You guys answered this in the review session last time. Yes?
Caching.
Excellent, yes, caching. So basically you cache the directory. That's the idea. And many existing systems do that, actually. They cache the directory locations. Of course, you need to now ensure that that cache is correct, right? So it's multiple levels now, right? You need to keep that coherent. You need to ensure that that doesn't go bad, right? But this is the way to reduce the access latency to the directory, having directory caches. Okay, we'll not go into the design of that now, but you can imagine how system design becomes even more difficult. How can you scale the system to thousands of nodes, given that we want to keep the directory small and minimize the access latency? That's the art of designing a computer system. Remember when I talked about computer architecture earlier, I said it's not science or engineering only, but it's also art. It is art. It's very difficult to evaluate the design options that you can come up with. It's just impossible as far as I can think of. Maybe someone will at some point design a machine learning technique that goes over all the possible choices and gives you information. But in the end, it's the human that's designing the machine learning technique. So even for that, it's difficult. So basically, think about some of these design options. And finally, can we get the best of snooping and directory protocols? I think that's a good direction to think about also. And then whenever you want to get the best of 2 things that are wildly different, what do you think of? What is a good principle? Heterogeneity, right? Maybe you have a heterogeneous protocol design. Maybe in some part of it, you employ Snoop-based protocols, and as you scale, you employ more directory-based protocols. So you could have a hierarchical protocol, for example, in chunks of your system. You have some processors that are connected via a bus, and you employ a Snoopy-based protocol. And across that a collection of nodes, you employ a directory-based protocol. Basically, it's a hierarchical system. Okay. Well, one thing to reduce the size of the directory, actually we briefly talked about this in the review session, I think. This is the data structure that you need for a directory. This is just a high-level view. But basically, for each address, you need to keep track of which processors have it and which processors have it in what state. Right? This is required to support invalidation and cache block requests. The real key operation to support here is the set inclusion tests. Basically, you would like to figure out which processor has the block. You'd like to have this information encode a superset of the processors that have that block. Right? You don't want the subset. You really want to have the superset. Superset is OK, which means that false positives are OK. You want to know which caches may contain a copy of the block. In that case, you send invalidations to that superset, and there will be some spurious invalidations. You will send an invalidation to a cache block, a cache, even though the cache doesn't have that block. That cache will basically ignore that request, and it will still acknowledge you saying that I don't have this block. This is OK. But false negatives are not OK. You cannot afford to have incomplete information over here. If processor 0 has the block and you do not record it over here, you'll get incorrect results, probably, at some point. Which means that you can actually optimize these data structures. You do not need to have exact information. As long as you have a superset of the blocks, you're good. So most accurate and most expensive one is having a full bit vector. Basically, for each processor, you have a bit indicating that that processor has it. But this is the most expensive, and that's full information, complete information. You can have compressed representations of that. People have looked into that. You can have a linked list representation. For example, if most blocks are shared by 1 or 2 processors, you could just record the ID of the processor, right, in a linked list manner. And if that's the case, you can have at most 2 IDs recorded in the directory. And then if you have more than 2 shares, one option could be to say, oh, I don't know, send invalidations to everyone in the system. Right? It's either you keep track of 1 share, 2 share, or it's everyone. Right? And if most blocks have at most 2 shares, that may be a good design choice, right? So that's one way of implementing this linked list. Or you can have a Bloom filter, as we've discussed, right? You can just have a small bit vector, and you can keep track of that Bloom filter. Although you need to do something interesting over here, because you need to, whenever you get a request for a block, you need to send invalidation request. And Bloom filter by itself doesn't tell you which caches you should send requests to, right? Because Bloom filter is just, you just set some bits, right? You need to decode them back to cache IDs. Anyway, you can think about this in more detail. But these are the tricks that you can play to reduce the size of the directory. Okay. Any questions? Thoughts? Okay. Let's move on to interconnection networks, because this is actually employed in many places. How many of you have taken networking courses? No? It's not business networking, it's networks. Computer networks. No, none. Maybe we should have required networks courses. It's good to know. Okay, maybe you've not covered this material anywhere. So basically, we're going to talk about interconnect, or interconnection networks, or networks in general. Interconnect is a special kind of network, as you will see. Basically, the basic goal is to connect components. And this could be very general. There are many examples. Like you could connect processors to processors, processors to memories or banks, processors to caches, or caches to caches, or processors to I/O devices. So this example shows that you have some nodes that have processors, memory, disk, and a network interface controller, and you have this interconnection network. And you could have cache coherence across all of these processors, which is supported by this interconnection network. This is what a distributed shared memory system looks like today. So why is this important? This is the third big component of computing, because it affects the scalability of the system, and it also affects performance and energy efficiency. And it could be critical in many cases, especially when you have communication over here. basically, what is scalability? How large of a system can you build? And how easily can you add more processors to the system? Performance and energy efficiency. How fast can processors, caches, and memory communicate? Right? How long are the latencies to memory? How fast you can synchronize between different processors? How much energy is spent on communication? So all of these are affected by the interconnection network. So there are 3 or 4 major properties of an interconnection network. We'll cover some of them. We won't go into more detail. These all can be multiple lectures each. Topology, routing, buffering, and flow control. I think these are tightly integrated. That's why I put them together over here. Actually, all of these could be tightly integrated. But topology specifies the way switches are wired. These nodes are connected. And we'll take a look at many different topologies today. It affects everything. It affects how do you route messages, how reliable is the network. If one link fails, what fraction of the network fails, what fraction of your system fails. It affects the throughput, latency, how easily can you build it. Routing algorithm basically says how does a message get from the source to the destination? How do you route that message? In bus it's easy, right? You broadcast to everyone sees it. This could have many properties, but it could be static or adaptive. We'll see that. Buffering and flow control. What do we store within the network? Do we store entire packets? Or do we transfer parts of a packet at a given time? How do we throttle during oversubscription? That's the flow control, basically. How do you stop nodes from injecting if the network is oversubscribed? You can think of the internet, for example. Internet actually does this throttling, congestion throttling. If, for example, there are too many packets going through a router, that router sends messages saying that slow down to the sources. Right? And this is tightly coupled with the routing strategy, actually, because how you do this flow control is affected by how you route messages. Let's take a look at topology first. I'll go through a bunch of topologies, because this is actually a pretty interesting area too. We'll start from the bus, and we'll go examine a bunch of different options. Not in this order. And then, well, let me cover the metrics, and then we'll talk about different topologies. Basically, there are a bunch of metrics to evaluate interconnect topology. The ultimate metric of everything is really, well, for performance, it's really execution time, right? These are just, for performance, it's execution time, and for energy, it's really system energy, right? But some of these actually help design a better system. So cost is, of course, important. We'll take a look at the cost of different topologies. Latency is important. Contention is important because they all affect, well, these two affect performance at least, and cost affect your performance efficiency. There are many others exist that you should think about that we're not going to cover. Energy, for example. How energy efficient is one network over the other. Bandwidth, and overall system performance, which is the ultimate thing for performance. Let's take a look at the bus. So bus is basically very simple, right? Actually, these are 2 different figures. Basically, you have these different nodes connected over a bus. And this is a more detailed example. That's what we've thought about. Basically, it's a single link. Because it's a single link, it's simple, right? And it's cost effective for a small number of nodes, because as you increase this size, it's not cost effective anymore. You need to develop a bus that actually can satisfy all of the requests. The other big advantage is it's easy to implement coherence on this, right? You get snooping and serialization for free on the bus. The downside, as we've discussed before, it's not scalable to large number of nodes because of 2 reasons. One is, well, I guess this is loaded here. You have limited bandwidth, and because of the electrical loading, you get reduced frequency over here. The second is you get high contention, so this network gets saturated and becomes a bottleneck very quickly. Think about node 0 wanting something from node 1. You cannot do that while node 2 and 3 are also communicating, right? Assuming you have the single link. You have to partition the bus somehow, which becomes a more different topology. Make sense? So you cannot have 2 transfers at the same time. That's a big problem if you want to design a scalable system. On the opposite end, you have the point-to-point connections. Every node is directly connected to every other. So 0 is directly connected to every other one. 1 is directly connected to every other one. 2, 3, 4, 5, 6, 7. There you go. This is nice because you get the lowest contention this way, right? Potentially the lowest latency also, if you can optimize these links somehow. And it's kind of ideal if cost is not an issue, right? Because everything is separated from every other one with one hop distance. You don't need to hop to another node to get to any node. The downside of this is the highest cost, right? Because you need a dedicated link between every node pair. As a result, you have ON square links where if you have n nodes. And you need to have also ON connections or ports per node, right? As you can see over here. So it's not scalable for this reason. Basically, it's not scalable for a very different reason than bus, right? And there's another issue, basically. If you actually have this, how do you lay it out on a chip? And if you don't have it on a chip, if you have across computers, how do you actually do the wiring, right? Actually, if you design a very large-scale data center or multiprocessor server today, that wiring is one of the biggest costs. You need someone, assuming you have electrical wires, you need someone to go around the room and wire these computers correctly, right? If someone actually messes up the wires and they place the wires from one computer to some wrong location, you'll get wrong results, right? A lot of reliability issues are actually because of that wiring today in supercomputers. If you look at top 500 supercomputers, for example, you'll see those computers wired to each other, and if you look at the wiring, it's like a huge mess. I should have found a picture over here, but you can find it on Wikipedia, for example. If you search for top 500, you'll see the supercomputers that are wired like a mess. And this only increases that wiring cost, right? Because everybody needs to be connected to everyone else. So I have many, many more wires. And if you have this on chip, now you have to lay it out on chip somehow. All of these, well, that's going to be difficult, right? You can have more metal layers on your chip, but then that increases your cost. If you have a 100-core processor, you probably don't have 99 metal layers on your chip. Okay, so this is not very scalable. So let's try to achieve this while reducing the cost. And Crossbar is one example to do that. In Crossbar, every node is connected to every other, again, similar to this, but only one connection can be used at any given time. Only one of the nodes can be using the connection at any given time. This enables concurrent transfers to non-conflicting destinations. Right? It could be cost-effective for a small number of nodes. So this is one example over here. Basically, you can see that every node is connected to every other one. For example, 7 is connected to 0 over here. And every other one is also connected to 0 through this vertical line. But only one at a given time, you can see that through this mux, can be sending something, or only 0 can be receiving from only one in a given cycle. But you could buffer these things such that they get pipelined, and 0 receives a request from every other node in a pipeline manner. So this is low latency and high throughput compared to a bus, obviously. The downside is, again, it's expensive, right? It's not as expensive as point-to-point, because it's not point-to-point anymore. You share some of the links between the nodes. You share the links to the destination, right? And it's, again, not scalable because it does have ON square cost. And it becomes difficult to arbitrate for these links as n increases, right? Basically, you somehow need to arbitrate for these links. I'll show you another picture soon, a more detailed picture of this. But for a small number of nodes, people have used this. It's actually used in core-to-cache bank networks in IBM Power 5s, for example, or Sun Niagara 1 or 2, and some other systems. But still expensive. These are expensive systems, actually. We'll see that more consumer-grade systems use rings, which are less costly. Like a lot of Intel and AMD systems use rings to connect processors because this is costly. Well, this is an example of a crossbar design. Basically, you have this link that connects everyone to node 0, and everybody basically has this gating signal, right, for that link. This is one example. And somehow, all of these nodes need to arbitrate such that only one of these gating signals get asserted, right? And that arbitration makes this a little bit complex, and we will see how many cycles it takes in IBM Power 5, for example, or Sun Niagara soon. Well, I guess Sun UltraSpark T2, which is Niagara 2. Basically, they have something very similar to this, except it's buffered. You can see the buffers over here. What they do is they connect 8 cores and 8 L2 cache banks. Let's see. These are the 8 cores that are connected to bank 0. Similarly, you have a crossbar link connected to bank 1, ... up to bank 8, and then also to the non-cacheable unit. Basically, it's a I think it's a 8x9 crossbar. And they have a 4-stage pipeline to ensure arbitration. This is what the arbitration network looks like at a high level. You request, you arbitrate, there's a selection process, and then you transmit a message. And for each source destination pair, you have a 2D queue buffer that looks like this to hold the data transfer request. Make sense? So all of the banks can transfer data. All the cores can transfer data to the banks this way, and all the banks reply to the cores this way. Okay. It's basically this with 8x9. Okay. You could have bufferless and buffered crossbars. This is basically this changes how you handle arbitration and flow control. Imagine a bufferless crossbar. In this case, you don't have buffers in the connection points over here. Basically, somehow these nodes need to arbitrate with some circuitry to determine which one transfers the packets. Right? Or you could have a buffered crossbar where you can add these buffers over here. Basically, each node sends its requests to the buffer, and then these buffers arbitrate over here. Right? You still need to have some kind of arbitration logic. But now you can simplify the design a little bit, because arbitration can be simpler, scheduling can be simpler, because you're doing it closer to over here instead of at the nodes. And you can do flow control over here. You can say, oh, my buffer is full, so don't send me more packets. That's the idea of flow control. You can have variable size packets, which we'll not go into. The problem is now you have n-square buffers, so your cost increases, right? Your complexity reduces, but your cost increases. We'll see bufferless and buffered networks later on again. Okay, any questions? It's fun. Okay, so, but this is expensive, as I told you, right? This is still expensive because it's ON square, right? And if you want to have a buffered crossbar, now you have buffers to deal with also. Well, can we actually reduce the cost of this? Can we get to a lower cost than a crossbar, yet still have low contention compared to bus? And people have developed the idea of multi-stage networks for this. They're basically networks that are indirect. Basically, you have some nodes here that just do the routing. These are the communicating nodes. These are the IDs of the nodes. That think of these as processors, let's say, and these are memory banks. You have 8 processors and 8 memory banks. That's how old multiprocessors used to be designed. You have these processors that are connected with these memory banks. And you have a switch now in between. What we've done is we've kind of partitioned the switches. So each switch is a 2 input, 2 output switch. And the connections look like this. The upside of this, let me give you the upside first. Now your cost is not n squared, right? It's really n log n, if you look at this, where n is the number of nodes. And you can think about why it's n log n. And your latency is log n now, right? Latency has increased a little bit because latency is not, well, if you calculate the latency of this, it's the latency depends on how wide your network is. Basically, on average, it's well, I guess it depends on how you communicate, so I'm not going to go into that over here. But here, your latency of one-way communication is O log n. If you have 8 nodes, it's really 3 stages. Right? And there are many variations of it, which we're not going to go into. If you take 742, we will go into some of them. Yes?
How do they maintain their timing constraints with these variable length networks?
Variable length links, you mean? Well, yes, that's a design issue that you need to solve. So if some of your links are really long, some of them are really small, that's an issue that you need to solve. You can pipeline the links, definitely. But that adds more cost, because now you need to have pipeline latches in the middle of your links. That's a good question. We'll see that issue in some of the other things. Okay, so Omega network looks like this, basically. So why is this less, this is less costly than a crossbar, obviously. But it's also not as high bandwidth. Let's take a look at an example. Let's say this processor 111 is transmitting data to memory bank 111 or requesting something on 111. It can only go through this link, right? It cannot go through any other link. Processor 000 may request the same data from a close by bank 110, not the same bank. But if these 2 requests arrive, and this is the only path you can take to actually request from 001 to 110, I believe. Yeah, you can convince yourself of that. if these two requests arrive at this node at the same time, you get a conflict, right? And these conflicts happen in many places. So you get a conflict even though the pairs that are communicating do not really have an overlap, right? So that's why these have more bandwidth contention, but they're much cheaper. This is another example of multi-stage networks. This actually looks like a butterfly, right? Anyway, so basically you have more restrictions on feasible transaction destination pairs, but these are more scalable than crossbar in terms of cost. It's N log N in this case. And each of these switches look like crossbars, right? You have a 2x2 crossbars. You're really building, instead of having an 8x8 crossbar, what you're doing is you're partitioning that network 8x8 crossbar into 2x2 crossbars and connecting them in such a fashion that you'll minimize the conflicts. And there are many examples of this which I'm not going to. This could be circuit switched, in which case, whenever you're sending a request, the first time you actually form a path and reserve that path. Let's say the processor 0 wants to send a message to processor 7. It basically reserves these crossbars such that no one else can use them. Now that's bad, right? If you do that circuit switching, no one else can use these crossbars until the communication between 0 and 7 completes. But it's simple, hopefully, because in that case, you don't need to have buffers over here inside. You don't need to do arbitration within the crossbars for every packet. If you do packet switching, basically you send your packets to each of these crossbars, and the packets hop from router to router pending availability of the next required switch and the buffer. So you can think of internet today as doing packet switching. So what's the difference between circuit switching and packet switching? Do you guys know about this, by the way? I might have covered this somewhere. Yes, probably 213? No? Okay, I guess I'll cover this quickly. But this is really the subject of a networks course. But circuit switching, the idea of circuit switching is you set up the full path and then do the transfer. Set up the full path means, well, let's go back to here. Let's say you want to transfer from 0 to 7. You send a control packet saying, I'm going to transfer from 0 to 7, so set up the routers such that they're connected. You can think of this as a programmable fabric. Think of this crossbar as programmable. Basically, when this crossbar receives this packet, it programs itself such that this connection is, only this connection is connected. Right? And then when this one receives the packet, it programs itself such that only this connection is connected. And when this one receives the control packet, it sets up itself such that only this connection is connected. Make sense? And then when you send the request, for example, or the data, it just flows through. There's no need to do dynamic routing. There's no need to determine, oh, where am I going to send this packet? Because you already set up the path, set up the crossbar to always transmit through this link, from this port to this port. Make sense? So there's no complexity of dynamic arbitration. Whereas here, you have packets and you always dynamically arbitrate. You say, whenever you have a packet that's pending in any of these buffers, you need to make a choice. Where do I connect this output? Which output should I connect to which inputs? Every cycle you make that decision basically. And if two of these buffers or two of these ports require the same output port, basically in that case what you do is you grant access to one of the ports, one of the input ports, and you deny access to one of the other input ports. As a result, you need to have arbitration logic if you have packet switching. Whereas if you do circuit switching, you need to have that arbitration logic because you've already set up the path. And if someone else requests that path, you say, too bad, I've already set up my circuit, so request again. Right. And which means that someone needs to tear down that circuit. This is called tear down in internet. Basically, once you set up the circuit, you establish that path. At the end of communication, you need to say, oh, I'm done with this, so you can allocate yourself to somebody else that requests you. That's how. So you need to have this overhead of handshaking, ensuring that you set up the circuit and then tear down the circuit. Whereas here, the overhead is really in the router. You dynamically arbitrate, but there's no setup, tear down overhead. So basically, circuit switching sets up the full path, establishes the route, and then sends the data. At that point, no one else can use those links that are established. Packet switching routes per packet. For every packet, it's routed individually, possibly via different paths. So this is more flexible. You don't deny service to any packets. Packets come to the routers, and you dynamically arbitrate. So it's more efficient in that sense. If the link is free, any packet can use it. Whereas here, if you go back over here, even if you've set up the path between 0 and 7, and someone else, let's say, let's pick one. Who else can use it? Okay, 5. 5 wants to use this. Even though 0 and 7 are not using this particular crossbar at this point, 5 cannot use it because only this is connected. 0 and 7 needs to tear down this path before 5 can use it. So that's why this is inefficient. Whereas with packet switching, both 5 and 0 and 7 can use this path. Right? Okay. So circuit switching, the upside is faster arbitration within the router, right, within the switch, because you set it up and then arbitration is easy, quick. There's no arbitration actually in a sense because you've already set up the path. The downside is now you need to set up and bring down the links or bring down the louders, this connection. That full path needs to be, there's control overhead, and this takes time. Packet switching, you must dynamically switch. Basically, you must dynamically arbitrate at each switch, at each router. So it's potentially slower at each router. And each router is more complicated because of this. The upside is there is no setup or bring down time. There is no control overhead to say, oh, I want this full path. Right? And of course, it's more flexible. It doesn't underutilize the links, as we've discussed. Because if a link is free, any packet can use it. So actually, internet uses both of them. You can have circuit switches or packet switches, but packet switching is more common. Okay, so the choice of circuit and packet switching is really independent of the topology. With any topology, you can do circuit and packet switching. It's really a higher level protocol on how a message gets sent to a destination. However, some topologies are more amenable to circuit versus packet switching, and we won't talk about that. Let's take a look at another example. This is the we've seen one multi-stage network, Butterfly. This is the Delta network. It looks similar, but it's really different, right? There's still single path from source to destination, but each stage here has different routers. If you look at them, it's not exactly the same. This one is different from this one because this one has a link that goes this way. This one doesn't have that link, right? So the patterns in which you get contention is different than this network. Actually, this is one of the earliest networks, earliest multi-stage networks, and this is another seminal paper from Illinois that discussed this network. And this was one of the first networks that was proposed to replace caustic crossbars as processor memory interconnect. Again, this was processors and this was memory. We're not going to go into the details of this. I just want to give you a brief overview of what networks could look like. This is another example. This is the Omega network. Again, it has single path from any source to any destination. But in this case, all stages are the same, kind of. We kind of route it different. This was used in the NYU ultracomputer. Okay, I can go on this, but let's stop here. The key idea is basically you're trying to approximate the benefits, low contention of a crossbar at a low cost. Let's take a look at the opposite end. How can we scale up the bus? So we talked about point-to-point links and then crossbar and then multi-stage networks. Bus is still far away. How can we bridge the gap closer to a bus? So the next step over the bus is a ring, basically. There's a big problem with the bus. It's not scalable, but ring is a little bit more scalable. And ring looks like this, basically. You have nodes that are connected to each other via small links, and you have stops on the ring, and they're connected this way in a circular fashion. The upside is it's cheap now. The cost is really ON because you really have N links. But the links are shorter in this case, right? You really have short links between each node. The downside, the big downside, is you have high latency, right? If you want to go from this node to the one that's in the middle over here, it should probably be put over here, but there should be a ... really. I don't know why it's not coming up. Basically, you need to traverse half of the ring. Right? That's a problem. It's not easy to scale. You don't need to know about bisection bandwidth. I guess I'll introduce it, but basically the bisection bandwidth is the maximum possible bandwidth that you get when you cut the network in half. And as you increase the size of the nodes, as you increase the system scale, as you add more nodes, that bandwidth remains constant. You're really not adding more bandwidth to the system in this case, right? Whereas if you're scaling a crossbar up, you're really adding more links. Here, you're not really adding more links that are shared by everyone. You're really adding more links between the different nodes. As a result, you get higher latency and probably more contention that way also. But these are cheap. These are more scalable than buses. As a result, they're used in many processors today. Intel still uses rings, but they're moving into hierarchical rings, as we will see. Intel's Larrabee processor, which I guess doesn't exist as much anymore. I guess it exists as many integrated cores. What is it called? Xeon 5, that's right. Yes. And IBM sells, and many commercial systems today actually use rings. So let's take a look at rings in a little bit more detail. This is a simple topology, it's simple implementation, and the router looks like this basically. This is a unidirectional ring. Basically, you can go through the link in one direction, and these arrows show the direction. A bidirectional ring now has another ring over here that connects things in two directions, or you can actually have double directions over here. But if you look at this, the router actually looks like this. You have a 2x2 router. It could be buffered or it could be bufferless. You get reasonable performance if n and perform needs are moderately low. Right? If n becomes high, now your latency increases. And this is the cost. This is the number of average hops. Latency now depends on utilization basically also, because it depends how many packets are injected into the network determines how much contention there is in the network. You're familiar with rings? So. I guess this is the first time you're getting exposed to interconnection network, so you're taking it all in. Okay, so how can you make this more scalable? Basically, one idea is to have bidirectional rings. Bidirectional rings mean that basically you have two directions on this, or you have another ring that goes the other way. Now you have a choice, right? You can reduce latency because you can figure out the shortest path, and you can inject. So for example, here, if you have a unidirectional ring, going from here to here requires n node traversals. Whereas if you have another direction, you just require one hop to go from node 0 to node n-1. That's the upside of a bidirectional ring. It also improves scalability for this reason. The downside is it has slightly more complex injection policy. You need to select which ring to inject a packet into, right? Or which direction you should send the packet into. And that could be determined based on the contention, how much latency there is, how many packets are on this side of the network versus on this side of the network. So you could have many different policies. Or you could do it statically. You say, I always inject to this direction if the node that I require the data from is numbered 0 through n divided by 2 minus 1. And I inject to the other direction if the number is higher. Okay. Now you can get more fancy. Basically, if you want to scale the system up, hierarchy is another good idea. Basically, you can increase the hierarchy. The idea is you can have hierarchical rings that look like this. Actually, Rachada has worked on this, so I can tell you more about this. But basically, instead of having, I should have had 16. Instead of having a ring that has 16 stops, you can have 4 rings that have 4 stops each. In this case, the latency within the ring is quick, right? Because you have only 4 nodes over here. And you can have another ring that is connecting these 4 different rings. Right? So this is the idea of hierarchy. You have the first level, in which you partition the nodes into nodes of 4, which are connected via local ring. And then you have a global ring that connects those collections of nodes. That's the idea. And you can actually have a bigger global ring, which has more connections. And even multiple rings over here that has more connections. You have 2 global rings in this case, right? If you look at this. This is more scalable because now you don't have a single ring connecting all the nodes. Your latency doesn't go up significantly. So your latency, especially within the local ring, is very short, right? If you want to communicate between the local rings and global 2 local rings, again, your latency is short. It's not as long as a single ring. Because you just need to hop onto this ring and then hop off in this ring, right? So it's more scalable and lower latency. As a result, there's a lot of interest in implementing this in industry today. And it's more scalable. This is, I think, a 64 node hierarchical ring system. That's one example, of course. So you have 3 levels of rings. You have the local rings. You have the second level local rings that connect these 16 nodes over here. And then you have the third level. Well, this is the global ring, you can say, that connects these each of the 16 node pockets. The downside is more complex now, right? It's not as simple as a ring. You add more complexity, more routers. These routers need to have different functionalities or more intelligent routing mechanisms. You can actually apply the idea of hierarchy to any kind of network. We just discussed actually one of them, right? I told you that processors that are close to each other are connected via buses, and then processors that are far away, you have these collection of processors that are connected via buses, and you connect them via rings, for example. Instead of a ring here, you may have a bus that connects 4 processors, and then you can have rings that connect these 16 processors, and you can have some other topology after that. So hierarchy is a concept that's used to scale systems to larger number of nodes. So if you want to read more on hierarchical rings, this technical report discusses the design and implementation of a mostly bufferless hierarchical ring. We'll talk about buffering, because when you have contention over here in a router, one key question is, what do you do to the packets? If 2 packets come to the router and they need to go out in the same output port, what do? There are 3 choices, as we will see, as to what you would do to a packet. You could drop the packet, one of the packets. You could buffer one of the packets, or you could deflect one of the packets. You could send the packet to somewhere else, hoping that it will find its way to its destination. Okay. So rings, the downside of rings is scaling them up to a very large number of nodes may become more complex because you need to introduce more and more hierarchy. So people have started looking into meshes. A mesh looks like this. Basically, every node is connected via small rings to every node around it. Well, at 2 dimensions, the 4 nodes around it in this case. This is a 2-dimensional mesh, that's why it's 4 nodes. So your distance from close by nodes is not too far, right? Because it's just one single link over here. Cost here is ON in this case. Average latency is O square root of N. You can do the calculations. It's easy to lay out on chip. It's regular and equal length links. Right? Basically, every node is connected to 4 of its neighbors: north, south, east, and west. I guess east and west. The one big upside of this is you get path diversity now. You have many ways to get from one node to another. For example, if you want to communicate between this and this, there are many paths you can take, as long as your routers can support it. Basically, these are nodes, the green ones are nodes, the yellow ones are routers. And you need to have a router that needs to do this arbitration. So the downside of this is now your routers become more complex. I guess we'll have it somewhere over here. Well, maybe we don't have it. So the downside compared to a ring is your routers are more complex. Because you can have 4 requests coming in, and you need to route them out to 4 possible different places, because these are bidirectional links. Okay, so this actually uses many on-chip network prototypes. Intel's single-chip cloud computer has something that looks like this. Tylera's 100-core processor has something like this. I believe they're selling these days. Make sense? Okay. So one issue with this mesh is it's kind of asymmetric on the edges, right? For example, if you want to communicate from this node to this node, you need to go all the way this way. Instead, wouldn't it be nicer if you actually had a link over here, such that you had perfect symmetry across this? And that's the idea of a torus, basically. Actually, mesh is not symmetric on the edges. Performance is very sensitive to placement of task on the edge versus middle. Basically, if you have this node communicating a lot with this node, and you, let's say you have 2 threads that are communicating a lot, and you place them over here, that's too bad. Your performance is terrible. Whereas if you place those threads over here, your performance would be great. So a torus, by adding one more link, well, I guess that goes this way, for example, or this way, it's symmetric across all of the nodes. Basically, you have 2 threads that are communicating over here, and you can place them over here, and they get connected via one hop. Basically, you wrap around the mesh. It avoids this problem. It gets even higher path diversity because you actually have more links that are added, and it gets higher bisection bandwidth. If you actually look at the cut this network in half, you see 1, 2, 3, 4, 5, 6, 7, 8 links crossing. And if you actually add the paths for torus, you'll have much more because they'll be wrapping around. You'll have 16 of them crossing, I think, in this case. Okay. The downside is higher cost. Right? Now you have more links. It's also harder to lay it out on chip. How do you actually do this? I'll give you an example of how to do that maybe. Because you have unequal link lengths as you brought up. I'm not sure if that's true. So this is one way of laying it out on chip. This is kind of like a torus in one dimension. Just one. If you take this and slice it out, this is what it looks like. You can actually weave the nodes to make internode latencies approximately constant. And you can convince yourself that this is that one dimension of the torus. Okay. What time is it? Should we take a break? Well, let's keep going. Let me finish the topology at least. Or do you guys want to take a break? All right, let's take a break. This is a good place to think. Let's take a break for 5 minutes and be back around, I guess, 52 according to that. And then we'll continue with trees. All right, let's resume because I want to finish interconnection networks today. And that's 52. That's good. Okay, so we've covered mesh and torus, which are more costly than rings, but less costly than multi-stage networks, maybe. Actually, it's not clear. Depending on the multi-stage network, they could be similar, right? There are other topologies. So if you think about this, now as you design this kind of topologies, your performance is very much affected by the placement of threads that are communicating. For example, I'll take this example. If you have threads that are communicating mostly locally, and if you place them into this ring, they can communicate really fast, right? This could be a bus also. So if you could localize your communication to parts of the hierarchy that are close to each other, that's great. These are good fits. That kind of computation is a good fit for this kind of hierarchical substrate. But if you cannot do that, if you place your task such that the one that this node needs to, the thread that's placed here needs to communicate with this thread, well, that's a lot of distance, right, to travel. So in all of these networks, keep in mind that where you map the tasks have a big effect on performance because that determines your communication patterns. If you know your communication patterns really well, or if you can dynamically identify those communication patterns, you can place or migrate the tasks that communicate a lot closer to each other in these networks to minimize the latency. Right? Trees are another kind of network. These were actually developed for something called reduction operations, and I'll briefly talk about that. Basically, it's a planar hierarchical topology that looks like a tree. Well, this is a tree, right? You guys know what trees are. It's basically a binary tree in this case. Well, this is a binary tree. That looks like a different tree. That's like a four node tree over here. The latency is log n. In this case, you have 2 levels or 3 levels of the tree. This is good for local traffic. If your communication is really between these 3 nodes, for example, then it's good, right? And this is an example of a fat tree. Fat tree because if you look at this, well, this is pictorial, but the link between the top parts of the tree is much wider, much higher bandwidth than the link that is down in the leaves of the tree. Why would this be the case? Because there's more communication potentially between these, right? You want to support that communication because there are many more nodes connected to this part compared to the nodes that are connected to this part, right? So that's good for local traffic. They're cheap actually. The cost is ON again, and these are actually easy to lay out. I'll let you think about. Well, this is an example, for example, here. Clock, for example, when you do the clock distribution, it's like a tree, right? The clock of a processor needs to be routed to all of the elements, and actually a clock tree looks kind of like this. Even though it doesn't transmit packets, it transmits the clock signal, right? A clock is an interconnection. The clock tree is an interconnection network too. It doesn't need to be designed as an H tree. It could be designed as a bus, except it's not scalable. If you want to have a single bus going through everywhere on your chip to clock your registers, well, good luck, right? That's a lot of loading on that bus. So that's an interconnection network too, right? except it doesn't. It carries something else. It's really the clock signal. So this is easy to lay out. The problem with trees is root can become a bottleneck, especially if you have a lot of communication. If your communication is kept mostly local, this is great. Again, but your root can become a bottleneck. As a result, people have developed fat trees, and this was Connection Machine that developed the fat tree, for example, that looks like this. You can read more about it. Again, if you take 742, you'll see this more. But this is, well, I guess I give you an example. You can read this technical report, which is kind of nice, that talks about how Connection Machine is designed. And this is what it looks like, basically. This is the tree. You have 4 nodes connected to these 2 nodes. This is actually a little bit complicated tree. It's not as simple. And the goal is to minimize contention. That's why there are 2 nodes that are connected over here. It's kind of randomized, right? You don't have this perfect tree over here. But in a sense, you have 2 head nodes within the branch. You can either go through this branch or this branch, right? And then you can go up to multiple head nodes over here as you go into the upper layers. So you don't have to reduce the contention that happens at the head node at the highest level. They actually try to distribute the load across these different head nodes over here. So there are a lot of other things that were employed over here, which we're not going to talk about. For example, multicast operations that were supported within the tree. If you want to if this node wants to send invalidate messages, for example, to processors 5, 7, 9, that's kind of a multicast, right? It's not a broadcast, but it's a multicast. You're sending the same message to multiple different nodes. And the tree had support for that. The nodes, these routers in the tree actually had support for that. By the way, these are, you can think of these as routers. These could be just routers, right? These are all your nodes, but these are really your routers. You could have nodes over here also. What kind of computation would fit nicely here? Let's assume that you're actually adding all of the elements in an array. And let's assume that you have 1 million processing nodes over here, 1 million adders over here, and you design an adder tree. Right? That's a great fit for this kind of substrate, right? Each node will add 2 numbers and send it up. The other node will add 2 numbers and send it up. Now you add the sum over here and send it up. And then somebody else adds the sum over here and sends it up. So that way you can have a hierarchical adder tree. And that kind of computation is very efficient on this kind of system. That's called a reduction operation. Basically, you're adding a bunch of numbers, for example. You can imagine other things also. It's kind of cute. But if you have some other communication patterns, maybe this doesn't fit as well. Okay, maybe this is the last topology I will finish with. And this becomes kind of like more complex. This is a hypercube, basically, and you can have multi-dimensional hypercubes. This is a 2-dimensional hypercube, 3-dimensional, 4-dimensional. And you can read more about it. I'm not going to go into the formalisms of a hypercube. But the upside of a hypercube is now you have latency OllogN. Number of links are actually n log n. And we haven't talked about radix, so don't worry about that. You get low latency. The problem with this is it's hard to lay out on chip. Take a look at what this looks like. It's kind of hard to lay out. But this was actually implemented in some old supercomputers called the Cosmic Cube. Was developed at Caltech in the early 80s. And this is kind of the 2D layout of the interconnect of the Cosmic Cube. The upside, well, they wanted really low latency of this. That's why they have this. I think this is a 6-dimensional cube. You can read it somewhere. Yeah, there you go. Binary 6 cube for the 64-node machine. And it was one of the earliest message passing machines. This was not shared memory, so these communicated through message passing. So you can read this paper, but I'm not going to assign it to you. If you take 742, this is kind of a teaser for 742. This is the kind of stuff that you may be looking at. It's fun. It's very hard to do this on a multi-core system and lay this out. That's one of the problems with it. Okay. Let's see. We still have some time. So we'll cover some other topics and hopefully we'll finish. So we've discussed this already. Basically, you have a router over here. You have 2 packets that are coming from different directions and they want to go to this direction. Basically what they are trying to do is they're trying to use the same link, same output port at the same time. What do you do? And as I said, there are 3 fundamental ways you can handle this. Obviously, you're not going to be able to send both of them. Actually, that could be a solution, but now you have multiple ports over there, right, for the same link, and you need to partition the link into two. Let's assume that that's not a solution because that increased complexity a lot. There are three fundamental solutions. You could buffer one of them. You could have a buffer saying, oh, I'll let you go, but you should wait and try again in the next cycle. You may or may not go in the next cycle because there may be something else, or there may be something buffered. You could drop one. You could say, well, I'm going to let you go, but I'm going to drop you, right? And you can basically it's a knack. You send a knack to the requester saying that I dropped your packet, resend it. Or you could misroute one. Misrouting is another possibility. You could say, oh, I cannot send you this way, but why don't I give you this other port? It's kind of nice, right? Because that port happens to be free. And figure your way through other routers. You can come back again, right? That's the idea of deflecting. Basically, you deflect the packet, misroute it. Misroute because this packet really wants to go this way, but you're sending it somewhere else. Right? This way, you can utilize these empty links, not busy links, and hopefully the packet somehow turns around and comes back, goes to its destination somehow, in some way. Right? That's the beauty of networks that have lots of connections. You can use these strategies. You can actually have combinations of this, right? Sometimes you do buffering. If your buffer space rounds out, or if your buffer stays close to the maximum, you start deflecting if you have not a lot of congestion in the other links. If you have a lot of congestion, you start dropping, right? You could combine these strategies. In fact, Internet does combine these strategies also. Internet, you usually do buffering, but once the router's buffer is full, it starts dropping. That's why you have, at the protocol level, these acknowledgements. TCP/IP has these acknowledgements, and if it doesn't receive an acknowledgement, it resends the packet, right? And it could misroute as well. So whenever you build a large-scale system, you need to handle contention somehow, and these are the three fundamental strategies. And these actually affect how the router is designed. We'll briefly talk about that. Because buffering is actually expensive in on-chip, whereas misrouting may not be expensive, because you may actually send a request to this node, and then the request can go to the destination via some other route. Right? You can actually handle contention in a simple way. Now, dropping may be expensive because, again, as we discussed over here, if you drop a packet of a sender that's really far away, now first you need to inform that the packet is dropped, or the sender somehow needs to resubmit its request, thinking that it's dropped, and then that resubmission takes time also. But this could be a good strategy when there's heavy congestion. Right? In fact, when a packet is dropped, a lot of the networks employ what is called exponential backoff. And the idea is, if you drop the packet, you resend the packet after some time. And if it gets dropped again, you back off a little bit, like you increase the time you wait before you send the packet, and you increase the time exponentially as the number of drops increase, such that you hope by increasing the time interval between your resubmissions, you minimize the contention in the network. Ethernet works that way. So there are a bunch of trade-offs over here which I would like you to think about, which we're not going to get into in much detail right now. So bufferless deflection routing is one example. I'll briefly talk about that because I kind of like this idea. Basically, the key idea is packets are never buffered in the network. This is an extreme case. It's a very old idea. Paul Baran proposed it in a technical report in 1962. It was considered for the internet, but you'll see one of the problems with it. That's why it wasn't employed as a sole solution. Again, these have different trade-offs. As a result, heterogeneity is a good idea. Using all of these solutions in some reasonable combination is a good idea. But the key idea of bufferless routing is you don't buffer them. When two packets contend for the same link, you deflect one of them. So let's take a look at this example. You have a 3x3 mesh. You have these two different nodes that are sending packets to this destination, and they happen to go this way. And they arrive at this router, middle router, and the middle router sends one packet to the destination, but it cannot send this blue packet because this link cannot be used by both packets at the same time. So it deflects this blue packet because it doesn't have a buffer. It doesn't do dropping, because dropping requires some support, right? If you drop, you need to have support for knacking and resubmission. Whereas this way, you don't require that support. Basically, this packet gets deflected, and this packet arrives to its destination. But because of the path diversity that we discussed, this packet can go back to its destination through some other route. Right? It takes longer, but makes it over there without being dropped and without having the cost of buffers over here. So if the buffers are really costly in your network, this may be a good idea. That's the idea, basically. And you can inject new traffic whenever there's an output, there's a free output link. For example, if this node is injecting, let's say toward here, let's say it needs to go, it needs to be routed over here. It can pick the free output link and it can inject anywhere. It doesn't need to go only one way. It can go this way, it can go this way, it can go this way. It just needs to detect a free output link. That's the idea. So the upside of this is, well, this is actually called hot potato routing also, because you can think of the packets as a hot potato, and no one wants to keep it because it's too hot, right? So when Baran introduced it, he called it hot potato routing. It's also called deflection. But basically, the big advantage is now you eliminate all of these buffering overheads, because once you have buffers, you need to have overhead to allocate buffers and deallocate buffers, and you need to ensure that buffers are not oversubscribed, right? That needs to have some flow control. You replace this buffering with this deflection routing logic, which is actually not that easy to design, but if you're interested in that, you could take Zone 42, for example. Basically, what you're doing with this idea is you're really buffering the packets on the network links. You're using the network links as buffers or temporary buffers, and packets always travel on the network links. They get latched in pipeline latches, but you don't have additional buffers for them to wait. Okay, let's talk about routing algorithms. Do I need to say anything else about buffer? There was something else. So the one downside of this is if things get congested a lot, if you have lots of contention in the network, this doesn't work too well because now all of the packets get deflected to different places, and you get even more congestion in the network. That's one of the reasons why this idea was not employed purely in the internet, because once you have a lot of injections into the network, there will be lots of packets that are running around in the network, if you will, and your network becomes full. It becomes difficult to inject into the network at that point. So you run into all kinds of fairness and starvation issues. Okay, let me continue. Routing algorithm, this is another property of a network, and there are three types of this. We'll briefly talk about each. Deterministic routing always chooses the same path for a communicating source and destination pair. You always go through the same path. Obviously, if you use bufferless routing, this is not the one you want. Because in bufferless routing, you always pick a path based on the contention. Oblivious routing chooses different paths without considering network state. We'll see an example of this. But bufferless routing, again, is not oblivious, right? Because you choose a different path by considering network state in bufferless routing, because you look at which packets are contending, and based on that, you determine the path. Adaptive, you can choose different paths adapting to the state of the network. Bufferless routing is this, basically. You observe the state of the network, and you choose the path based on that. And how do you adapt? It could be based on local or global feedback. You could say, oh, this part of the network is really congested, and I have this information because that information is collected with some control packets. So I'm not going to send this packet through that. Let's say this node is going to send a message to this node, and it knows congestion information. It says that all of these nodes are congested. So it can send the packet such that it goes through this way. That's adaptive routing. Or if these are congested, it can send the packet through somewhere here, if it's possible, right? That's the idea. So of course, this requires more information. You could do minimal adaptation with minimal path or non-minimal path. Minimal path is the minimal distance between a source and destination. You could keep that minimal distance, or you could say, oh, I'm going to tolerate a longer path just so that I can avoid congestion. That's non-minimal. Bufferless routing is non-minimal, right? That's what I described to you, because it obviously sends a packet to a direction it shouldn't really go to, ideally. Okay, let's take a look at deterministic routing, because this is actually the simplest one that's actually employed in many systems. All packets between the same source and destination pair take the same path. There's only one path you could take. And the simplest one is dimension order routing. Basically, you order the dimensions and you route in one dimension first and then the other dimension next. XY routing, for example, what you do is you first traverse dimension X and then traverse dimension Y. If you're communicating, well, I guess I made a mess over here. If you're sending a packet from here to here, you first traverse dimension X, go to the Y coordinate of the destination, and then packet gets routed through the Y coordinate. And the response goes through this way. You first traverse the dimension x and get to the y coordinate of the destination, and then get routed that way. It's very simple, right? So the routing logic in the routers is very simple in this case because there is no adaptation that happens here. It's also deadlock free. We'll see that deadlock. Deadlock is a big issue actually when you design networks because you may oversubscribe the resources, and once you have cycles in the resources, you may have no forward progress in the network, which is dangerous. The downside of this is it could lead to high contention, right? Because if most of your communication is between nodes that are here and nodes that are here, you're really not utilizing these links over here because you're doing x, y, x, y, x, y, and then y, x, y, x, y, x. And all of these links over here are not utilized. Right? You're not basically making full use of the path diversity in the network. Well, these are kind of the same thing, actually. So what is deadlock? Let's take a look at deadlock. Deadlock means no forward progress. It can happen in many places, but it's always caused by circular dependencies on resources. Basically, this is one example. Each packet waits for a buffer occupied by another packet downstream. Here, in this example, packet 2 wants to go here, but packet 3 is occupying the buffer that packet 2 needs. Packet 3 wants to go here, but packet 4 is occupying the buffer that packet 3 needs. Packet 4 wants to go here, but packet 1 is occupying the buffer it needs. And packet 1 wants to go here, but packet 2 is occupying the buffer it needs. Now you have circular dependence between these packets and nothing can move. And whenever you have buffers, you run into issues like this. This is deadlock. And this happens because your routing algorithm doesn't avoid the deadlock, and maybe you haven't allocated the resources nicely in a reasonable way such that you ran into deadlock. So how do you solve problems with deadlock? There are three actually major solution directions. One is avoiding cycles in routing. The problem over here happens because packets can go x, y, and yx in both directions. As a result, you can have the circular paths. Whereas dimension order routing says packets can always go x, y, x, y. So there can be no cycles in the resource allocation. That's one way of avoiding. If you want to think about it, I'll suggest a paper to you. Basically, restrict the turns each packet can take. You can take turns from, if you're coming from the x direction, you can turn to the y direction, but not the other way around. You cannot come from the y direction and turn to the x direction, basically. That just doesn't work. Okay? In a slide, I'll show you a paper related to that. And if you want to learn more, 742 is a good course. Or you can avoid deadlock by adding more buffering, escape paths. You can somehow say you have many more buffers such that you will never run into this situation. You can escape, basically. Or you can somehow detect and break the deadlock. Once you detect somehow that there is a circular dependency, which can be pretty hard because that dependency can exist as a huge cycle, right? But if you can detect it, once you detect it, you can preempt the buffers. You can say, oh, packet 3, I'm going to throw you out such that this deadlock is broken and everybody can make progress. Okay. Well, this is an important problem when you design networks. But this is the turn model. This is the first solution, avoiding cycles in routers. And this is a seminal paper that introduced it. But basically, you can design your routing algorithm to avoid this deadlock. You can analyze the directions in which packets can turn in the network. You can think that if packets are never turning, that deadlock problem actually never exists. If you have a linear network, you should really not have deadlock in there unless you have some other problem, because everything should keep moving linearly, right? And you can determine the cycles that such turns can form and prohibit just enough turns to break possible cycles. XY routing does this, basically. You cannot have the circular dependency because packets cannot turn from the YX direction. And you can read this paper. This is a little bit more theoretical, actually, but it's fun. Let's talk about oblivious routing also. This is actually a very famous algorithm, Leslie Valiant, developed by Leslie Valiant. He won the Turing Award, partly due to this work. But this is an example of an oblivious algorithm. Oblivious algorithm means you can take different paths between a source and destination pair, but the path you take is oblivious to the state of the network. Well, random. The goal with the oblivious algorithm is to balance the network load. Why? Because remember, with the deterministic algorithm, we don't have a good load balance. If you're communicating always between these two, you're always utilizing these links and you have contention. If you somehow randomly route some packets to some other part of the network, you get better load balance. So the idea of this is you randomly choose an intermediate destination to route the packet to, route it there first, and then route from there to the destination. So between source and intermediate to destination, you can actually use dimension order routing. And I'm not going to that. The upside of this is now if you select a random point in the network to route to first, you're really randomizing the load, right, in the network. Basically, whenever you're sending this packet over here, you first pick a random node in the network. Let's say random node is here. You first route there, and then from there, you route here. And another node is communicating with another node. It first picks a random node in the network. It first sends a packet there, and then to the destination. That's the idea. This kind of randomizes the load across the entire network, which is great for load balance. And when you have congestion, it could be OK, actually. The downside is non-minimal. Packet latency can increase. And this is especially bad if there's nothing else in the network, right? If the network is empty, why are you routing this packet and increasing your latency? Right? So people have proposed optimizations to do this in high load and to restrict the intermediate node to be closed. But we'll not talk about that. But these are the kind of issues that 742 will discuss a lot. Adapter routing. Let's talk about the adapter routing also. Well, we still have time. Is this interesting to everyone? It's pretty cool, right? Actually, a lot of these strategies have been used in the internet at some point also. So adapter routing is basically the most complicated one. The idea is you can have multiple paths between the source and destination, a source and destination pair, but you adapt the path. You choose the path based on network state. And it could be minimal adaptive or non-minimal adaptive. Basically, in a minimal adaptive routing, router uses the network state to pick which productive output port to send a packet to. So a packet can have a productive output port or a non-productive output port. Productive output port means this is the output port the packet needs to minimize the latency to the destination. And there could be multiple output ports, right? You could actually have multiple paths. For example, going from here to here, there are multiple paths that have the same latency. This path and this path, at least two paths, right? It's the same latency. And you can pick the minimal one, that both are minimal. You can pick the one to take based on the congestion state. It could be global congestion state over here. It could be local congestion state over here. Right? Okay. So this could be aware of local congestion or even global congestion. The downside is minimality restricts achievable link utilization. Basically, you can only pick between multiple non-minimal paths, which is not the same as the total number of paths, because then you do not choose this path, for example. Right? That path goes all over. You cannot do that because that's minimal adaptive. That's not minimal adaptive. So non-minimal adaptive is really the fully adaptive routing. This is the most flexible form of routing. Basically, in this case, you need to misroute the packets somehow or drop the packets to non-productive output ports based on network state. And bufferless routing does this. The upside is it can achieve better network utilization and load balance. The downside is, well, there's another problem. Now, actually, non-minimal adaptive routing mechanisms usually don't have deadlock at the lowest level, but they have another problem, which is live lock. What is live lock? Basically, all of the packets are making some progress, but they're not making forward progress. They're moving, but they're not reaching their destinations. That could happen in this case, right? If you don't have guarantees to ensure that all of the packets arrive to their destination within a bounded amount of time. Because what could be happening is you have some packets that are circling around and never reaching their destination. So you need to somehow ensure that this doesn't happen. And that's a problem. How do you do that efficiently? Okay, I'll introduce you to on-chip networks and then we'll finish. Basically today, so all of these topics were the subject of large-scale multiprocessor computers until early 2000s, actually. But today, since we have very large-scale integration, we can put multiple cores on a chip. So all of these interconnect topics have moved into on-chip. You also have off-chip communication that's needed if you want to scale up the system even more. But on-chip networks connect cores, caches, memory, and controllers. Because buses and crossbars are not scalable even within the chip. And this is an example over here. You have routers over here, and you have processing elements, which could be different things. You could have packet switching or circuit switching, but many of the on-chip networks that have been developed are packet switched today, but actually they have circuit switch components too. 2D mesh, two-dimensional mesh is most commonly used topology because it's actually easy to lay out. And they primarily serve cache misses and memory requests and coherence requests. Well, cache miss is a coherence request, actually. So this is one example, and this is one example of a router, which I will not go into, but in 742 we can actually cover that. Let me go over the advantages and disadvantages or constraints of these different types. What do you have on chip that's different? On chip, you have low latency between cores. There's no ping constraint. This is actually important. Because if you go off chip, you need to actually have ping constraints. So some of the topologies you implement may be limited by that. You have a lot of wiring resources, and they're very rich. Off-chip interconnect is very expensive, power hungry, and you cannot switch it very quickly. Right? Whereas on-chip interconnect, it's on chip, right? You could add more and more of that. You could add on top of each other. You could have multiple layers of metal. You have very high bandwidth as a result of this, in addition to low latency. And you can do simpler coordination also within the chip because the latency is low, right? You could say, oh, I'm going to coordinate the requests of all of these routers such that they can do better synchronization. You can have constraints and disadvantages on the on-chip. The downside of on-chip is now you have a two-dimensional substrate, right? Off-chip, you can build any substrate you want. You're just wiring these different things. On-chip, you have two-dimensional. Actually, you could have three-dimensional too if you could do 3D stacking. And energy and power consumption is a key concern on chip because you're limited by the power you can supply to this chip. That's why your interconnect needs to be efficient. As a result, complex algorithms are less desirable on chip. And logic area actually constrains the use of wiring resources on chip. You cannot have all these huge wires. So there are a bunch of different characteristics, but we will not talk about this over here. But I'll leave you with this, actually. You really need energy efficiency on chip as well as the off chip. Basically, there have been results that show that these interconnects actually consume significant power, both on chip and off chip. These are some results from Intel, for example. Approximately 28% of the chip power in the single chip terascale computer was consumed by the on chip network. I believe IBM has similar results to Intel SCC. And this is a really old prototype of an on-chip network. That's why it has lots of power consumption. But basically, it's good to look into very energy-efficient designs. And energy-efficient design actually requires a lot of optimization of the topology, routing, buffering, flow control. So you need to design the entire network such that it's energy-efficient. And I don't think I will cover this, but I can take questions if you want, since we have only 1 minute. So there are a bunch of different research topics in interconnects and design topics which I will not go into. But part of 742 is about this, because it's parallel computer architecture. Any questions? Or you're ready to go back and work on your lab 7? Okay, I'll see you Wednesday.